So chapter 2 is all about first order differential equations. And we're going to talk about, in the first section, a numeric approach of solving differential equations. And then we'll take a look at the more symbolic ways of finding, symbolic techniques of finding differential equations. So the graphical approach is to take a look at these things called solution curves, which are the solutions to the differential equations, but graphically as a curve. And for us to do that, a good place to start is these things called slope fields. So we have to figure out what a slope field is. First of all, we want to relate the idea of a derivative with, remember last time we talked about it as a rate of change, but graphically we can look at the derivative as a slope. So if we can get our differential equation into, I think it's called normal form, where the highest derivative is solved for by itself, then we have something that we can look at as what we would call a slope field. So if we get dy dx on its own, or y prime, then the right-hand side would be a combination of x and y's. Some of those differential equations might just have an x, or some of those differential equations might just have a y. But in any case, we would be expecting a combination of x's and y's on the right-hand side of the equation. So if we're able to write our first order differential equation that way, we have what's called a slope function or a rate function. So a direction field or a slope field is a graph of the first order differential equations that shows a slope at any particular point. So let's take a look at an example. Maybe y prime is equal to x times y. Okay, so you have y prime is equal to something, so this is a slope function. And we can try to graph this by plotting points, right? When you first learn how to graph, when did you guys learn how to graph? Fourth grade? You have y is equal to something with an x, and then you say, well, what if x was this, then y is that? What if x is something else, y is something else? So we could start off doing that. We can make ourselves a table of, now this is kind of weird because we have x and y's, but that's not what we want to graph. We want to graph the slope. So the output is kind of like the slope. So we can put y prime or dy dx, whatever. And then on your input is not just the number x. Remember, the right-hand side has x's and y's. So your input would be points, pairs of numbers, x's and y's, right? So if we take a look at this example, let's pick some points on the xy plane, like 0, 0. That's always a good place to start. If we pick 0, 0, and we plug that into our equation, what's y prime going to equal to? 0. In fact, if we pick any combination where one of them is equal to 0, we're going to get zeros for those, right? Kind of boring. So let's try other numbers, non-zero numbers. So let's say, what if we had 1, 1? What's your y prime going to be? 1. 1 times 1, right? That's the input-output kind of thing. So the slope is 1. Let's try another point, like 2, 1. This is going to be 2. Let's try a negative point, negative 1, 1. Negative 1, negative 1, negative 1, positive 1. This is getting too long. So let's just pause here for a moment. And we have a list of numerical values and some slopes. So we have a list of points and slopes. And so we want to put this together into a graph. So what we could do is we can draw our XY plane, and then the way to graph this by hand, which I'm not going to be expecting you to do, but you guys are going to be using computers to graph this, but I want you to be able to look at the graph and say, oh, that's a graph of this particular differential equation. So the way to graph this, if you're graphing this by hand, is to go to the point that you put in there, and instead of drawing a point or whatever, you're going to draw a slope. How do you draw a slope? You're going to draw a small little line segment that describes slope. How does a slope of 0 look like? I just went like this. It's a horizontal line. So a slope of 0 has a horizontal line, right? So I'm going to go to the point 1, 0 and draw a horizontal line there as well. I'm going to go to the point 0, 1 and then draw a horizontal line. So it looks like anywhere where either the x or the y is equal to 0, I will have horizontal lines. Okay, now the non-zero. Let's go look at the interesting parts that are non-zero. 1, 1. At the point 1, 1, what's our slope? So let's draw a line segment that has kind of like a slope of 1. So y is equal to x has slope 1. So if we imagine drawing a line like that, that has slope 1. 2, 1. So 1, 2, 1. At 2, 1, what's your slope? Your slope? So it's a little bit steeper than that, right? Kind of hard to tell, but that's why it's better to have a computer generate this for us. If we go to negative 1, 1, negative 1, 1, that's over here. What's the slope? Negative 1. So that's going down. And then negative 1, negative 1. We're in the third quadrant now. Slope. Okay. So you can imagine how these things might look like. If you draw a few more. Okay. So this is a slope field. This is how a slope field would look like, more or less. And what happens here is that these are the slopes of your differential equation at any particular point. And so if we're going to try to trace out a possible solution for this, what we might do, maybe I'm jumping ahead of myself. I should go back and take a look at the notes. But what we're going to do is we're going to go start a particular point and then try to see from that point, I'm going to go forward and then I'm going to imagine what the slopes of these things would look like as I go forward and forward. And then it looks like if I go farther and farther away from the origin, this thing's going to get steeper and steeper. And so this is a possible solution curve. And when we're looking at solution curves, by the way, when we're looking at things in math, we're always going from left to right, from the lesser to the greater, from negative to positive. So maybe somewhere over here would be going down. So it's going to depend. And this is a really crappy picture, but we're going to take a look at a computer-generated picture to help us actually get a good visual. All right, let's see if there's anything else in my notes that we need to add on. There's some slope fields. Let's just go jump to a slope field. So I think if you just Google slope fields generator, slope field, there's a um, bunch of slope fields that you can use. Which one should we use? Let's try Desmos. So if we have a particular function that we can put on there, like g of x, y is equal to, this is 2x divided by y, this is how your slope field is going to look like. Let's take a look at our example. X times y. So this is our example of, this is how our slope field would look like. Okay, and some of these things have special features. So here's a movable point. If you move this point around, you can try to figure out what your slope is, or how your slope would look like relative to the other parts of the other pieces here. Okay. So let's, here's some of the ones that I looked up a few semesters ago. I'll put that in our notes. GeoGebra doesn't have it anymore. Oops. What happened? There. All right, so if we take a look at that particular example that we have, this is how the slope field should really look like. Oops. Sorry, I'm trying to move this. Oh well. Okay, the other thing that I wanted to get at was that from these slope fields, you can find a specific solution. And so one of our solutions, or the solution, a particular solution is something that we can get if we had an initial condition with your differential equation. So remember what that called, what that thing's called? We have the differential equation and the something put together and make up a something. What are those two somethings? What? Initial condition a differential equation, and then you tack on an initial condition, and then what should you get? A what? You would get a particular solution, but the whole thing is called an initial value problem, IVP. So a differential equation with an initial condition is an initial value problem, and if you have an initial value problem, IVP, then you can get a particular solution. So let's take a look at this this GeoGebra here. This slope field, x times y was our. So what happens here is that if you move your point to any particular point, you know the initial condition, you can see the initial condition as if it was a point, right? We established that. And so if we have an initial condition, we can treat it like it was a point, and then you can move it to a particular place that would give you your curve, your solution curve. Okay? So that's going to be an important part of doing these slope fields, is that for you to be able to find a solution curve, you can do the slope field, you can put the point down and then follow that point wherever it might take you. So with a graphing program like this, you can actually draw it all out. Let me copy this again and put it in our notes as another example. I'll fix that later. Okay. So let's take a look at some examples of trying to draw slope fields and find solution curves for them. So let's say this is your differential equation. You have y times dy dx equals negative x. And then let's do first task is to try to draw a slope field. And after you draw a slope field, then we can try to use these initial conditions to see if we can find particular solutions. Okay, with the GeoGebra graphing program here, we can draw multiple solution curves for different initial conditions. It looks like we need to do something first, though. What do we need to do first with our differential equation? Yeah, so let's divide by y so that we can write it in normal form. So dy dx is equal to, it'll be negative x divided by y. All right, so that's our differential equation in normal form. So if we graph that, negative x divided by y, and then let's take note of the first one. Y of 1 is equal to 1. What is that point? This one? It's just be 1, 1, right? Just looking at the point. So x is equal to 1, y is equal to 1. So we're looking at the point 1, 1. If we just take a look at this without any solution curves, if you look at it carefully, it looks like it's pretty circular, doesn't it? It looks like there's a bunch of circles going on here. And then we try a solution curve where some weird things are happening. There we go, 1, 1. We get something like that. Why do you think that happens? Some weird thing happening there. You think that's really the curve? So there is a disadvantage in using technology, and you have to know when these things are happening. And what's happening here is that the solution to this differential equation is, in fact, a circle. And whether it's the top half of the circle or the bottom half of the circle, that's yet to be determined by your initial condition. And what this attempts to do is that it takes, here they say it takes steps of 0.1 to go from one point to the next point. And so these steps might be a little too big for this. Like when you guys draw a graph on your graphing calculator, you draw x squared, y is equal to x squared. Your graph isn't really drawing a parabola. Your graphing calculator is really plotting a bunch of points and then connecting the dots with a bunch of lines. And so if you try to do y is equal to x squared in your calculator, and then you make your steps really big, you're not actually going to see a parabola. Okay. So the same thing's happening for this. If we make this a little bit smaller, then we might get a more precise. Did I? Step size 0. So this one is a little bit smoother than the last attempt at it, but it still goes off. It looks like it goes off, vertically off to infinity. It really doesn't. So there's a little step that happens there where it just shoots off and it looks like it goes off to infinity. But it looks like it's just going to be the top half of the circle. So a solution for this differential equation looks like it's going to be y is equal to the square root of 1 minus x squared. Wait, 1? It's probably not 1. What is it? What's the radius of the circle? It's what? 1.5 squared? I don't think it's 1.5. It's close to 1.5. Square root of 2. Right? The 0.11 is on the circle. So you can deduce somehow that your radius is square root of 2. All right, let's see what the other point is. So let's draw another curve, 0, 4. Wait, 0, 4? 0, 4. So let's draw another solution. Let's take this point. 0, 4. Is that on the x-axis or y-axis? It's on the y-axis. 0, 4. There we go. Again, the little noise on the outside of that is because of the error that whenever things go off to infinity, computers and calculators kind of fudge things a little bit, so they make little errors like this. I was hoping that we would get another example that's below the x-axis. So let's make up another example here. Let's call it C. Oops. And then say y of 2 equals -3. So let's 2, -3. Let's put 2, -3 on the graph. -3. So 2, -3 now is a semicircle in the bottom half of the xy plane, so that it becomes negative. Okay. So let's imagine that little piece of stuff on the outside, the noise on the outside is not there. And so here are possible solutions for the different initial conditions that we have. So let me take a picture of this and put it on our notes. And then, let's see, do you guys have any questions? No, we're all good. My computer's responding really slowly today. All right, let's try to do a different one. Actually, you guys got the hang of this, right? So this is actually a worksheet assignment for you. Have you guys looked in the worksheet area? So I think last time I did it was we worked on it in a group in class. So let me decide whether it's going to be on your own or in the group. But I think since I'm doing this already, I think you guys can do this on your own. So I'll rework the instructions on the worksheet where you have to do this. You just download, or not download, just go to a website that has these graphers, these slope field plotters, and then GeoGebra is the one where you can put up to 4 initial conditions there. So let's not do this anymore. And let me just tell you, for that differential equation that we were working on, the solution to this differential equation looks like it's actually an implicit solution. And it'll be a family of curves, one parameter family of curves. So it's going to be x squared plus y squared is equal to some constant c. And you could try to see if you could take the derivative of this and compare it to the differential equation. And you guys remember implicit differentiation? You take the implicit derivative of this and then put it back into the differential equation. You'll see that that's going to be a true differential equation. And then you can try putting in values like 2, -3 in here, and then you solve for c, and that's how you're going to get the radius. Okay? All right, so that's the deal with slope fields. Let's go to the next part of this section, and that's section. We're still in section 2.1. Let me just copy everything here. So there's a lot of terms that we're going to need to get used to. First of all, the definition. An autonomous differential equation is a differential equation, first order differential equation that has the derivative, y prime, and then you can set that equal to the right-hand side, but the right-hand side does not have any x's. So there's no independent variables present. Okay, when you have a differential equation like this, it's called an autonomous differential equation, and it turns out that it's kind of easier to work with because the slope fields have a special feature. And we'll take a look at a slope field when we take a look at examples of these types of differential equations. In any case, since they have no x's in them, we just work with the dependent variable y, the function that we're looking for. So if we set this equal to 0, f of y equal to 0, it's like setting the slope equal to 0. What do you remember from Calc 1 when you set the slope as equal to 0? It's minimum or maximum, or changes something, right? It's a critical point. It's equal to 0. It has slope 0. So whether it's a minimum or maximum is yet to be determined, because like the cubic function is, anyways. When f of y is equal to 0, the y values that you get there are called equilibrium points. So your graph is going to hit one of those equilibrium points, or could possibly hit one of those equilibrium points. Okay, what are some facts about equilibrium points? If C is an equilibrium point, then y is equal to C is a constant solution. If C1 and C2 are critical points and C1 is strictly less than C2, then there's going to be no other critical points in between them. And solutions must be strictly increasing or decreasing, because remember, we're following these things from left to right. So if we follow from left to right, your graph is going to come from either an equilibrium point or infinity. It's going to come from there, and it's going to reach an equilibrium point or go off to infinity. Solutions must be strictly increasing or strictly decreasing. In other words, we're not going to have a solution curve that goes up and then comes back down, like the circle. We're not going to have any of those types of things. It's either going to be strictly increasing or strictly decreasing. Critical points are asymptotes. So the critical points that we find from the autonomous differential equation are actually going to be asymptotes. Okay, a few more definitions. Solution curves are asymptotically approaching a critical point from top to bottom and from bottom to top. Then that particular critical point is called an attractor. If the asymptote from left to right, if the curves are going away from the asymptote, then it's called a repeller, or it's unstable. And then if from the top it goes down, or in the bottom it goes down, or something like some combination like that, then it's called semi-stable. Yeah, that means it's going in the same direction. They're both strictly increasing or strictly decreasing. So maybe all these terms feel a little abstract right now. Let's see if we can come up with an example. Let's do the simple example where we have y prime is equal to some constant, 3 times y. So, by the way, do we know what the solution to this is? What? This is the differential equation where we say that the rate is proportional to the function. The rate of change of the function is proportional to the function. It's kind of like those population ones, right? So, any ideas what the solution might be now? It's exponential. Okay, we'll see that in the next couple of days. But let's say this is our differential equation. Let's take a look at the slope field for this. And what's interesting is that if you look at the slope field, see if you find if you notice a pattern, 3 times y, that's our slope field. Enter. I don't know if this is dramatic looking. And I don't know if it's best to zoom in or zoom out. Maybe we'll zoom in. What? No, that was find. Oh man, blew it. Let's try this one. It's not changing. There it goes. Um, do you notice a pattern? How can I adjust this? Anyways, yeah, do you notice a pattern? Yeah, Ramsey? If you fix yourself a y value and then you go along the x's, you see that the slopes are all the same, right? So if you take a look at the y value, different y values have different slopes, but if you focus on just the one x value, then you see all the y values there. So that tells us a couple of things. One, this thing doesn't depend on x, which according to the definition of an autonomous differential equation, there are no x's involved. So it doesn't depend on x. It only depends on y. So our graph then, you can really just take a snippet from one of the x columns, right? Now let's imagine a solution curve going through this. Let's see if we could do it by hand. Let's imagine how a solution curve might look like. It kind of depends on where you are. If we're starting over here, maybe over here somewhere, then your graph might look something like this. That's probably a bad looking solution curve. But then if you go on the negative side, it looks like it's going to approach, it's not going to touch the graph, but it's going to approach the graph, right? And then if you're further along over here, kind of like the same thing is going to happen. And then if you're in the bottom side, your graph is going to look like that. Or if you're over here somewhere, okay? Now, we have to take a look at this one at a time. So if we're looking at it from left to right, well, let's do some of the algebra first. If we set 3y equal to 0 and y is equal to 0 is a critical point, or they call it an equilibrium point. So y is equal to 0 is an equilibrium point. Oh, what happened? That means anything above that is going to stay above, anything below that is going to stay below, and none of your graphs will cross over to 0. Okay, so that's one of the things that they mention in those in the properties. The other thing is that whether you're above or below, your graphs are either going to be strictly increasing or strictly decreasing. Right? We see that here too. And then the equilibrium is an asymptote. We see that here too, right? Now, this particular equilibrium, if you go from left to right, what's happening to the graphs above it? Is it getting closer to it or going away from it? Going away from it, right? And then if you look at the graphs below, is it getting closer to it or going away from it? Also going away from it. So the graph looks like it's increasing on top and decreasing in the bottom, so it's going away from it. And so this equilibrium point can be considered as a what? A what? It's an asymptote, but in terms of some of the language that we're using here, so it's going away from the graph. So this is a repeller. This particular equilibrium is a repeller, or an unstable equilibrium. Okay? So the more interesting ones have multiple zeros. So we have 3 or 4 zeros, and then you'll see that if you draw the slope fields for that, you'll see the asymptotes, and you'll see if graphs are repelling, or if the equilibrium is a repeller or attractor, or the case where it's going both ways, it's a semi-stable. Now, this last bit of information here talks about a one-dimensional phase portrait. Since we only need to take a look at one column of it, so if we take a look at just one column of it, we can kind of see the information that we need to see, whether a graph is going away or towards the equilibrium. So what we could do is we could take a look at a one-dimensional phase portrait by drawing a one-dimensional graph, marking your equilibrium, and then from this graph, are your graphs going away from it or going towards it? So again, the question was, if it was above the x-axis, is it going away or is it going to the graph? To the equilibrium. It's going away from the equilibrium. If you're below this, are you going away or towards it? You're going away again. Or you can say that the graphs above are increasing, the graphs below are decreasing. So you can see here that this is repelling, and so it's an unstable equilibrium. Okay. All right. We have less than 5 minutes, but I want Yasmin to make her announcement, and then the rest is something that you guys can look at home, do for homework or whatever. We come back, we'll talk more about, we'll finish this section up, and then we'll go into 2.2. Okay. Homework problem. Okay, Yasmin took my class last semester, so this is really fresh for her, and she knows the kinds of things that I do in class and the kinds of things I put on the exams. So she would be a really good resource to take advantage of. And being involved in the STEM Center can be those clubs. You can also tutor. I really, I can't, I can't say enough how tutoring really helps you as a student. So especially if you run into Calc 2 problems and you practice your integrals, and so when you come into this class, you have those integrals kind of fresh in your mind, not last semester or 2 years ago, whenever you took Calc 2. Okay, good. All right, so that's it for now. Keep an eye out on what might happen to the worksheet assignment. It's not going to be due on Thursday, but it'll be due sometime soon. So I'm going to make some tweaks on it, and then you guys can take a look at it. Yes.